Welcome to 5.4 Chord and Arc Relationships. In this lesson, we're going to talk about the relationship between chords, arcs, and central angles. We're also going to look at when arcs are congruent. And there's two cases when arcs are going to be congruent to each other. And then we'll look at a last rule that relates chords and central angles. So first, let's talk about congruency, and let's review angles. Remember, two angles are congruent if they have the same measure. For example, you see A and B. Angles A and B are both 45 degrees. They have the same measure, so they are congruent to each other. So we can write angle A is congruent to angle B. Okay, but that is not the case for arcs, so let's take a look. So you see, if I zoom in, we see segment BC, which is a radius, and segment BA, which is also a radius. They're joining together at endpoint B to make a central angle, which is a right angle, and it's 90 degrees. So the minor arc AC is also 90 degrees, because remember, the minor arc has the same measure as a central angle. Okay, let's look at our circle E. Minor arc DF has the measure 90 degrees, because the central angle is 90 degrees as well. Okay, so we see arc AC is 90 degrees and arc DF is 90 degrees. So both of these arcs have the same measure, but if you look closely, they are not congruent. You can see that arc DF is actually bigger than arc AC because DF is in a bigger circle. So it's going to cover a same fraction of the circle, but it's just a bigger circle. So it's obviously going to be a bigger arc. So when are arcs congruent then, if it's not when they have the same measure? Well, let me zoom in. Two arcs are congruent if they belong to the same circle or congruent circles. Let me move this. There, that looks better. Okay, so if they belong to the same circle, which is what we have in situation A, you see that arc AB and arc CD, they both have central angles of 45 degrees, so their measures are 45 degrees. That means they are congruent because they are in the same circle. Okay, so that means arc AB is congruent to arc CD. Now, it is also the case if they are in congruent circles. So you see arc AB has central angle 120 degrees, so arc AB is 120 degrees. Arc CD has a central angle of 120 degrees, so its arc CD will be 120 degrees. So they have the same measure, and they are in congruent circles. So because they're in congruent circles, they will be congruent to each other. So AB congruent to CD. Because remember, it's not just because they have the same measure. They have to be either in the same circle or congruent circles. Because if they're in different circles, which is what we saw here, then they will not be congruent. They'll actually be different lengths, even though their measures are the same. Okay? So we're going to look at two ways to determine if arcs are congruent. So the first way is if you examine their central angles. So this rule states, if two central angles are congruent, then they form congruent arcs. So for example, I wrote it with pictures. If angle BCA, which is a central angle, is congruent to angle ACD, which is another central angle, then the arcs that form them are congruent to each other. So arc AB is congruent to arc ED, okay? So that's one way. You look at the central angles, and if they are the same, then their arcs will be this congruent. Second way is if you examine their chords. So this rule states two arcs are congruent if and only if their associated chords are congruent. So to provide you with some background information, I wanted you to know that every minor arc creates a chord. For example, if we just had arc AB, which you see here in yellow, if it has endpoints, right? The arc has endpoints. If we connected their endpoints, as so, like so, if I can get it to connect, yes. If we connect their endpoints, that will form a chord. Remember, a chord is a line segment where two endpoints are on the points of the circle. So every minor arc is going to create an associated chord. Okay? So let me switch colors. So this states two arcs are congruent if and only if their associated chords are congruent. Now I highlighted if and only if because this is a biconditional statement. This means it can go both ways and they depend on each other. So for example, if we look at the circle on the left, if arc AB is congruent to arc CD, then chord AB is congruent to chord CD. So that's going one way. You can also go in the other way and say, if chord AB is congruent to chord CD, then arc AB is congruent to arc CD. Okay, so you can see how this rule can go both ways. Now for this rule, we're going to look at a proof. But because you can go both ways, you can actually look at a proof for both ways. Okay, but in this video, I'm only going to go over one proof. So let's take a look. So we're already given, actually I should have this in view just for the beginning. So we're given the same figure, right? And you see the hash marks? So we're given that arc AB is congruent to arc CD. And it's given looking at the hash marks. So what do we want to prove? Well, if arc AB is congruent to arc CD, then chord AB is congruent to chord CD. But we want to prove that then part. We want to prove that chord AB is congruent to chord CD, okay? So that is our goal of this proof. We want to prove that the chords are congruent. So let's go ahead and do that. Let me zoom in. So first, let me start off by drawing the center. And I want to connect the center to points on the circle. And I'm going to label the center M. Well, again, oops. Sorry. Okay. So what are these segments called? Remember, they are radii because they are line segments where an endpoint is on. Oh no, I hope that didn't. Okay. So they are all radii. All four of these segments that I just drew, they are all radii because they have an endpoint on the center and an endpoint on the circle. Okay, so our second statement is going to say segment MA, segment MB, segment MC, and segment MD are radii. And what is our reasoning? Our reasoning is that they are segments with an endpoint on the center, and a point on the circle. And that's just the definition of radius. Okay? Sorry, I keep zooming in and out. I have to zoom in to write neatly, so. Okay, so because they're all radii, what can we say about these line segments? Remember, all the radii are congruent to each other. So MB is going to be congruent to MA, which is congruent to MD, which is congruent to MC. So that's actually our third statement. MA, MB, MC, MD are congruent. And why are they congruent? Because they are all radii. And we know that all radii are congruent because it's just the distance from the center to a point on the circle. And we said that all the points on the circle are equidistant from the center. They are radii. Okay, what else do we know? Remember, let's think back. I said there were two ways to determine if arcs were congruent. You either look at the central angle or you look at the chords. Well, we're trying to prove that the chords are congruent, so that's probably not going to help us. But we do know that the arcs are congruent. And based on those two ways, we can conclude that the central angles for those arcs are congruent as well. So central angle would be BMA. Let me draw it here. This angle, that's a central angle for arc AB, is congruent to DMC, which is this central angle. That's a central angle for arc DC. So they are congruent to each other. Why? Because we know that the arcs are congruent. They told us the arcs are congruent. So if the arcs are congruent, then their central angles are congruent. Okay? Now, what do you notice? Remember, think back to our postulates for congruent triangles. This is a side angle side congruency. So because we see three parts that are congruent and they match up to one of the postulates, we can conclude that the triangles are congruent. So triangle A, I just want to make AMB it is congruent. It is congruent. Let me make sure I get the angles right. CDM. CMD. Yes. Yeah, I'm pretty sure that's right. Now I'm confusing myself. Okay, yes. Because remember, when we write congruent statements, we want the vertices to correspond to each other. And what is the reasoning again? Because of the side angle side postulate. Because we have two sides and an included angle that are congruent to each other for one triangle to some other triangle. So we conclude that the two triangles are congruent. So now, just imagine we have two triangles. I know there's a lot going on in the circle, but just imagine you just see two triangles. So now what? You can actually conclude AB is congruent to CD, which was the goal. We wanted to conclude that these chords were congruent to each other. So that is actually our last statement. AB is congruent to CD. Why? Because corresponding parts of congruent triangles are congruent. CPCTC, right? So segment CD corresponds to segment AB, and since these are two congruent triangles, those corresponding parts are congruent to each other, right? Just as segment CM corresponds to AM, and since they're congruent triangles, those corresponding parts are congruent to each other. Okay, so that was one proof. So let's get into the last rule, congruent chords and central angles. This rule states that two chords are congruent if and only if their associated central angles are congruent. Okay? So again, if and only if, this is a biconditional statement, so this can go in both ways. So if you look at the circle on the left, if the central angles are congruent, then the chords are congruent. If the chords are, so that's one way. And then you can also go the other way. If the chords are congruent, then the associated central angles are congruent. So you can go both ways. So this is a way to determine, you see, this whole lesson is about the relationship between central angles, chords, and arcs, and how those relationships can help us determine congruency. So now let's get into some examples.